Hi everyone, Chris Tisdell here again. Thanks for tuning in. In this presentation, I'm going to continue my series of videos on linear systems and simultaneous equations. In previous presentations, we talked about the cases where you have two equations and three unknowns. We looked at an example where the planes involved cut along a line, or where the planes were parallel, so there was no solution. And in this presentation, I'm going to complete the cases talking about where the two planes involved are identical. So let me share my screen with you and we can get down to business. Okay, now, no matter what kind of linear system you're looking at, you can always perform these operations to reveal and simplify the situation and reveal the nature of solutions. Okay, you can interchange equations, you can multiply an equation by a non-zero number, and you can add a multiple of one equation to another equation. Now, this is the system that we're going to look at. I like to label my system, so the equations. You can see x, y, and z are the unknowns, and you've got two equations. Now, geometrically, each of these equations represents a plane. So what does it look like geometrically? Well, I've shown you this before, where you have two planes, and basically you have one of these cases. You have the planes touching each other along a line of intersection. You've got an infinite number of solutions. The planes are parallel, but they don't touch each other. In that case, the linear system has no solution. And in fact, the one that we're going to look at today is the third case. You're going to have parallel planes, but they're also identical. So they lie on top of each other. And again, you get an infinite number of solutions. So let's work through this example using some of the operations that we know we can do. And then I'll show you a nice GeoGebra plot of what's going on at the end. Okay, solve the following linear system. Well, you can see that the second equation is basically twice times the first equation. So these two equations are basically one and the same equation. To see that, you could divide the second equation by 2. So that'll become x, that'll become negative 3y, that'll become 3z, that'll become 2. You've got one and the same equation. Okay, another way of doing it would be the following. You could look at equation 2 and you could take 2 times the first equation away from equation 2. So here basically you'll get the same equation up the top, and you'll get 2x minus 2x, which is 0x, negative 6x plus 6y, 0y, and you'll get 6z minus 6z. Okay, now this is trivial. So let's concentrate at, say, equation 1. Okay, now it doesn't matter which one you choose here. I just chose equation 1 because the numbers in front of the unknowns are a bit simpler. Okay, now what are we going to do? Well, I'm going to introduce a parameter for y and a parameter for z. All right, so I'm going to let y equal mu and z y equal lambda and z equals mu. All right, now what I'm going to try to do is get x in terms of lambda and mu. All right, so let's go back to 1, rearrange, make x the subject. Okay, so that's a 3 and that's a z. And what I'll do is I'll back sub in for y and z, and I get this. So now I've got x in terms of lambda and mu, y in terms of lambda and z in terms of mu. I can now write this as a vector parametric form for a plane. So this case is going to give us two identical planes. We sort of knew that already just from the because one equation was twice the other equation, so they have to be the same plane. But now we're actually showing that in a little deeper way. So let's write down x, y, and z as a vector, and this will actually reveal a parametric vector form for the equation of a plane. Okay. So I'm going to write x, y, and z as a vector. And I have lots of videos on this, on parametric vector forms for lines and planes. Okay, so let's write x out as that, and then we'll break it down into its various parts, and that will give us the equation of a plane. Okay, y equals lambda, z equals mu. Okay, so what we're going to do is break this up, bring the 2, 0, 0 out the front. I'm going to then look at the lambdas and bring the lambdas out the front. So it'll be 3, 1, 0. And likewise with the other parameter mu. So I've got a mu there and a mu there. And I can have negative 3, 0, 1. And here, these are my parameters. Okay, so what is this then? Well, it is a parametric vector form of a plane that passes through the point associated with this vector and is parallel to these two vectors. Okay, so the infinite number of solutions lie on the plane that passes through, say, the point A and is parallel or contains to the vectors, let's say V1 and V2. Okay, so this is a case where you have identical planes. Okay, so if you want some more on parametric vector forms of lines and vectors, I have lots of videos on that. Go to my Introduction to Vectors playlist. But what does this look like? What does the solution look like? Again, glad you asked. Let me use Geogebra to show you what these things look like. Okay, Geogebra is awesome because it is free and it now has 3D plotting capabilities. So here I've put in x minus 3y plus 3z equals 2. Now, if I sort of naively type the second equation down here and press return, oh, nothing's really changed. You can see if I, and it simplified the equation for me too, but it's just the same plane. Okay, it's definitely the same plane. Okay, so there you have it. That is the case where the two equations represent identical planes. You have an infinite number of solutions. The points are just lie on the plane themselves, the identical plane. Hope you enjoyed this presentation. Join me for more presentations in the future. In the next video, I'm going to talk about 3 equations and 3 unknowns. So you've got 3 planes. Now they can interact in all sorts of crazy ways. So I hope you can join me for that presentation. Thanks for watching, everyone. Bye.